Right, welcome back. This is Linear Algebra Week 11, Friday, 29 October. So we are now beginning Chapter 8, Eigenvalues and Eigenvectors. For this, I'm going to suggest you guys to begin reading or watching this video from 3Blue1 Brown first. This is an amazing video. It's already 5 years old. And of course, it starts with this interesting recap, okay? And eigenvalues and eigenvectors is a very difficult topic, but what he says is true. It isn't so bad. So let's hear what 3Blue1 Brown say, and I'll comment on some of the things that he has said, so that it may bring some insight.
Particularly complicated or poorly explained. In fact, it's comparatively straightforward, and I think most books do a fine job explaining it. The issue is that it only really makes sense if you have a solid visual understanding for many of the topics that precede it.
Right. Can someone type on the chat? Can you hear the sound as well, please? Right, thanks. I'll continue.
Most important here is that you know how to think about matrices as linear transformations. But you also need to be comfortable with things like determinants, linear systems of equations, and change of basis. Confusion about eigenstuffs usually has more to do with a shaky foundation in one of these topics than it does with eigenvectors and eigenvalues themselves.
Right. So in fact, among all these four things, the first one that you really need to understand is linear transformation. Without that, then it's quite impossible to do this later on. And then after that, determinant. And for determinant, we are only going to be doing 2x2 or 3x3 matrices for exams. So that's all you need to know. And with this tool, you'll be able to solve most of the problems in the exams and what your understanding. And in the final part, the change of basis, there's the last few questions on the tutorial, and that is also quite difficult, right? So maybe we'll continue to listen to him first on the eigenvalues and eigenvectors, and then I'll bring you up to speed on transformation.
To start, consider some linear transformation in 2 dimensions, like the one shown here. It moves the basis vector I hat to the coordinates 3, 0, and j hat to 1, 2. So it's represented with a matrix whose columns are 3, 0, and 1, 2.
Now, this is a very interesting diagram, because basically you have a matrix 3, 0, and 1, 2, and you're going to use this matrix to transform some vectors. So for example, I have 3, 0, and 1, 2, and let me call this A. And then I have a matrix x1, x2, and then I would call this x, and then I would get y1 and y2, and I call this y. So you can think of this as a transformation of x from R2 to R2. So we are taking x as an element of R2 space, and we're moving it into another the same dimension R2 as well. So x is the input of the transformation, which is represented by the matrix A. So that's the glory details. And now he's telling you that we can interpret this matrix 3, 0, 1, 2 with a deeper insight. And the insight that he's showing you is this.
But you also need to be comfortable with things like determinants than it does with eigenvectors and eigenvalues themselves. To start, consider some linear...
Now, all these squares that you see and all the points that you see is the input space. And now he's asking you to look at 2 points, the green point, the green vector. So in this case, maybe I should just be very precise. So the green guy, the green vector is 1x, and this x is 1, 0, right? And the red vector is another x, a different x, and this is 0, 1. And we typically call this the J hat. And for the green vector, we typically call it the I hat. That's its notation. The green vector moves along the horizontal axis of we call it the x-axis by 1 unit. The red one is by 1 unit on top. And these grids are what he draw to say that this is the origin, this is 1, 0, this is 2, 0, 3, 0, and so forth. And of course, we can have any values in between. So this is the Cartesian plane. And the most important point is that the origin is known to you. Where is origin? And the green is some arbitrary thing which you say move right by one side. But the origin is fixed. Okay? Now, when we act on this green point, we'll move the green point somewhere else. When we act on this red point, we'll move the red point somewhere else. What do I mean by acting on it? That means we substitute this green point as x and we'll get a different y. We substitute this red point in as x and we'll get a different y. That's what we mean. So it is obvious that if you do ax, then you are doing this guy, and and then because it is now obvious that you are actually only taking the first column, right? You're only taking the first column because the other guy is 0. So this is 3, 0. And then if you play with the other guy, the same A, and then now you're taking the second column of A. Okay? And then you say, so what's so big deal about these two pairs of what do you call that? Coordinates, I hat and J hat. And later on he'll show you that actually all you need to know is this, how A moves these two guys, and then you'll know how A moves everyone else. And that's the beauty of this what do you call it? This video.
Linear transformation in 2 dimensions, like the one shown here.
Now, I show you that the green guy has moved to 3, 0. So you count 1 point, 2 point, 3 point. So the gray grids are the original points, and now the blue and the white grids are the new points. So we see 3, 0 here, and then the red guy is 1, 2. Okay, and then the grid basically has changed from a small square grid to this parallelogram. Okay, so the interpretation of AX is now moving all these square grids into a new square grid. Okay, so that's linear transformation.
It moves the basis vector I hat to the coordinates 3, 0, and j hat to 1, 2. So it's represented with a matrix whose columns are 3, 0, and 1, 2. Focus in on what it does to one particular vector, and think.
All right, now we take this yellow guy, and then we are now going to do A multiplied by the yellow guy. And you will see that the yellow guy will move, right? That's the whole idea. Will be transformed. And not only is transformed, it's linearly transformed, because by AX, this is a linear equation.
Think about the span of that vector, the line passing through its origin and its tip.
Now, it's going to tell you that if I give you a vector, a yellow vector, this yellow vector has a span, because any linear combination, sorry, not linear, any scalar multiples of this yellow vector lies along this line. So this pink line is the span of this given yellow vector.
Most vectors are going to get knocked off their span during the transformation.
This is a key idea. Every time I play with A multiplied by the yellow vector, most of the time, the resultant yellow vector will not lie in the same span. Okay, and now he's going to tell you that for eigenvectors, it's going to lie in the same span. That's the key idea.
I mean, it would seem pretty coincidental if the place where the vector landed also happened to be somewhere on that line. But some special vectors do remain on their own span.
Now, this vector is 1, -1. Now, this guy multiplied by this vector will land, what do you call that? So let's calculate, okay? So let's not get ahead of ourselves. Let's try. So now I'm going to use a different color, and let's do it in blue. And our matrix is 3, 0, and 1, 2. And then I'm going to multiply by 1 minus 1, which is the yellow guy. All right. So therefore, it is actually 3, 0 minus 1, 2, which is equals to 3 minus 1 is 2. And this guy is minus 2. So where's 2 minus 2? 2 minus 2. So the yellow guy will stretch to this point. Okay, let's see.
Meaning the effect that the matrix has on
Now,
such
it's
a
wonderful, isn't it? Basically, he shifts the whole grid, yeah? And then this yellow guy stretches to this point. And I mean, we did it on one point, and we saw that it's actually this yellow line becoming larger to end at this point. But he showed it even more beautifully for the whole grid, yeah? Any point, actually, if you know the original position, you will shift to the new position by this new grid.
vector is just to stretch it or squish it, like a scalar. For this specific example, the basis vector I hat is one such special vector. The span of I hat is the x-axis, and from the first column of the matrix, we can see that I hat moves over to 3 times itself.
Now, he's also telling you that the other vector the other vector. So now so this is one vector, one eigenvector. Okay, the other eigenvector that he's telling you now is that any vector that lies in the direction of 1, 0. So you say, hey, it just becomes 3, 0. So what did he do? He make that 1, 0, and then he's going to stretch it, transform.
Such special vector. The span of I hat is the x-axis.
Now, I hat is this green guy. The span is the whole horizontal line.
And from the first column of the matrix, we can see that I hat moves over to...
So the resultant vector still lie on this yellow line. So therefore, by our definition of eigenvector, later on we'll tell you, any vectors after linear transformation lying on the same span is an eigenvector. So that's the key idea. Now we see it graphically. The green guy is 3, 0. Where's 3? 1 point, 2 point, 3 point, lying on the horizontal line because the vertical axis is 0. Okay. Now, what about -1? Okay, let's try. Now, if I say this line along this direction is the eigenvector, what about pointing to the other guy? So this is -1, 0. And of course, this is obvious. Now it is a vector that lands and points to the other side. Okay. So eigenvector is just a direction. Whether it is pointing to this direction or opposite to it, meaning the negative of the whole value, it remains as an eigenvector. What about this guy? So I'm giving half the unit length. And then the answer is 1.50. Still pointing to the same direction. So all these guys are eigenvectors. Yeah, but of course they are just pointing to the same direction. And typically we want norm 1. So you either give me this guy or this guy is fine. Yeah, it doesn't matter which direction you point, but as long as unit length. Later on, you see that MATLAB gives the eigenvector in unit length. So later on, what about this guy? What is the unit length? So this guy, 1 minus 1, is an eigenvector. What is this? So let's call this V. And what is V over norm of V? To get a to get a unit length vector. So it is 1 over square root 2, 1 minus 1. And the answer is, this is 1 over square root 2 minus 1 over square root 2. So any vector that is a scalar of this vector is an eigenvector. Okay. Now, so before I jump, I would just want to show you that if you have MATLAB, you are just going to use MATLAB as a calculator and just do sanity check. So what do? First, I set A equals to this matrix in MATLAB. And then I'm going to generate two values. The eigenvector, let's call this P, and we call this P with P1 for the first eigenvector and P2 with the second eigenvector. Okay, now, what is surprising to you now is this. Oh, not surprising. Let's look at this. The matrix A multiplying by an eigenvector, something interesting happened. The eigenvector is stretched by, in this case, 3. Okay, so if P1 is 1, 0, there's a number 3 there. So let's call this D, and we're going to have 3 here, okay, associated with this guy. That means we know that if we send P1 into A, then P1 will be stretched by 3. What about the other guy? I stretch this by 2. See, 1 minus 1 become 2 minus 2. The input is 1 minus 1. The output lands exactly in the same span, in the span of this vector, and is stretched by 2. Okay, so the other guy is 2. Now later on, we'll figure out why we put this is called the eigenvalue, and this is called the eigenvector. So basically, MATLAB very quickly let you do this. PD is equals to the eigen decomposition of A. Finish, right? So if we now try to do MATLAB, I will show you what MATLAB does. Now, let's make a wild guess. We expect P. We think that P will be what's the value? 1, 0, I guess. 1, 0. And we expect the other P to be 1 minus 1. 1 minus 1. What about D? D would be 3, 0, 0, 2. Let's see whether MATLAB gives me this. All right. And so I type A is this, and I type this decomposition, and I get, what do I get? P is 1, 0. So first P is 1, 0 is correct. The second one is not correct, for me anyway. But what? Then you realize that no, actually it's the same. This guy is 1 minus 1. This guy is minus 0.71. So actually, what he did was that he gave me minus 1 over root 2 plus 1 over root 2. Actually, it is a vector of unit length pointing to the opposite direction. D, I get it correct. Okay, so don't be confused when MATLAB gives you this answer, because a vector, he's saying this vector points to this direction. That's all, right? You can point to the opposite direction, but it's still along the same span. And then MATLAB gives you the normalized version of it. Okay, I didn't give you. So that's the key difference. All right, now I'm going to pause for a little while and take questions. Okay, so in this first slide, I have I have used 3 blue, 1 brown example to show you the linear transformation, introduce you to what is eigenvector and the eigenvalue, which is basically a number that will tell me how much my corresponding eigenvector will scale. Why do I say that? Notice this picture here. P1 is scaled by 3, P2 is scaled by 2. So every time we talk about an eigenvector, we want to know his corresponding eigenvalue, or the other way around. Given the eigenvalue, we want to know his corresponding eigenvector. Okay? Now, all right, let's proceed. So this is the chapter. This is the chapter in Lay's book that you must read. And again, in this, so Lay couldn't animate, of course, in his book. So what did Lay do? Lay gives you this matrix A, which is 2 by 2, and then A is acting on U, A is acting on V. Where is U? U is this guy, which is minus 1, 1. He used a dotted line to show that after AU will move from here to here, while AV, which is 2, 1, 1, 2, will move from here to here, lying on the same span as V. So the conclusion is that V is an eigenvector, U is not an eigenvector. The other conclusion is that we want to see whether the resultant eigenvector, how was it scaled? And we call that the eigenvalue. Okay. The other thing about eigenvector and eigenvalue is eigenvector cannot be 0 because A multiplied by the 0 vector is the 0 vector. So then you say it's a scale version of itself. So we want to say a non-trivial eigenvector. Okay, non-trivial means 0. The 0 vector cannot be an eigenvector. All right, let's proceed. So we are done with this. And maybe now, okay, so I will continue my exposition. All right, so one is so let's list down some key points that we have already mentioned. What? Eigen, value, and vector only for, okay, the first thing is square matrix. You cannot find the eigenvector and eigenvalue of a non-square matrix. Okay. 2, the typical equations that we would start with is AX equals to lambda X, then N, X is not equals to the 0 vector, then X is an eigenvector. What's lambda? Lambda is the scalar. Okay, lambda. Actually, it can also be the complex. Okay, later on we'll figure it out. And yeah, currently X belongs to Rn if A is Rn by n. So A is a real matrix, square matrix of dimension n by n. X is a vector of Rn, but if we have time, we'll actually deal with X is a complex vector. Okay, and A can be also a complex vector. All right, so if this equation holds, then X here is an eigenvector and lambda here is an eigenvalue. Okay, so that's all. We are given A, that's what we are starting. And if this equation holds and x must not be 0, then we have just found ourselves the eigenvector and eigenvalue. Right? How many are there? How many eigenvectors value? Okay, right. So if you are lucky, you can have n distinct. If the matrix is n by n, you can have n distinct. But if you don't have distinct, you can have repeated. Okay, also later on we'll understand what's distinct and repeated. Eigenvectors up to n. Okay, you can have up to n eigenvectors. You can even have 0 eigenvectors. Okay, so that's very strange. I mean, for the real case. All right, for the real vector space, meaning that we are considering only x is belong to R. All right. So so we have just start here, and then now what? Okay. For the eigenvector as shown in Lei's book and Tribhuwan Brown shows eigenvector, or any scalar version of the eigenvector will result in ax equals to lambda x, meaning that the final answer lies in the same span of the eigenvector x. About number 5, what are the things you want to know? What is eigen? So eigen is a German word. Sometimes they say it's a Dutch word. And it is by its own, on its own. What on its own? So let's have a statement. An eigenvector of a linear transformation ends or remains a multiple of itself. So here is the word on its own. Okay, so I repeat what I say. Number 4 and number 5 is the same. Ax equals to lambda x. Lambda x is a multiple of x. It lies in the same span of x. The German word eigen means its own. Own what? It's multiple of itself. Okay, that's why. All right. Now, some books will tell you that there are when you ask how many eigenvectors and values are there, then they would have to ask you whether you are discussing the problem in the real space or in the complex space. If it is a complex space, then the answer is different. If in the complex space, you have n eigenvectors and an eigenvalue. In the real space, no, sorry. Yeah, but let's not go there first, okay? Let's ignore this problem first until we reach there if you have time. Okay. Right. Maybe I would now just show you a very simple example why I would just say that sum y, okay? Y some matrix do not have a complete set of eigenvectors. Okay, let's try. A is equals to 0, 1, minus 1, 0, x1 and x2. Oops. What is above? Now, if I multiply A by 1, 0, what do I get? 0, 1. So I have rotated my matrix, sorry, my input vector, and it now land where? It now land here. So I have moved from this point to this point, or maybe I should just say this point. I have moved 1, 0 along the horizontal axis to 0, 1 on the vertical axis. What about the other guy? A times 0, 1, I will get minus 1, 0. So what am I moving? I'm moving from this point to this point. So I am performing a rotation anti-clockwise by 90 degrees for all my points. Now, therefore, at any point in this R2 space, it has moved by 90 degrees. And there is no chance that you can get a vector that remains in the same span, because that's what this matrix did. He is going to rotate everything. He's going to rotate everything. Okay. All right. But then you say, does it have an eigenvalue and an eigenvector? In the real space, no. Okay. But what about the complex space? So let's try. A equals to 0 minus 1, 1, 0. So this is my matrix. And PD equals to eigenvalue of A. And I told you that in the real space, he doesn't, but in the complex space, we have a eigenvector that is in complex numbers, and the eigenvalue is also a complex number. All right, that's very cool. And you can, that's why, I mean, in the previous slide, I say that it depends on which space you're working on. MATLAB will give you the complex numbers because, yeah. All right. Okay. So I think with that, I'm almost done. And if I have, I'll leave the mechanics. Okay. So once we have a big overview, then the next problem we want to solve is page 4. How to find eigenvalues and vectors given A. So in the exam, we are going to deal with only these two kinds and special matrices. That means there are certain special matrices like upper triangle and the lower triangle that you have some tricks to find the eigenvalues and eigenvectors more easily. But typically, we only deal with these two cases. Now, how to study all this is I'm going to release the tutorial 8 support. And in this support, let me find for you. All right, so this is tutorial 8 support. I would first is, yeah, you can find the solutions, which I've already released anyway. I show you the 3 blue, 1 brown example today. And then, right, these slides will give you all the glory details of how to calculate the eigenvalues and eigenvectors. You can go through any one of them that you're happy with. And next Monday, I will go through one of them in greater detail. Okay? And you need to know all this, how to calculate the 2 by 2, 3 by 3 eigenvalue and eigenvectors. All right, so all these links are examples in YouTube, which I found to be relatively easy to follow, at least the mechanics of it, to find the eigenvalue and eigenvectors. All right, and so you have to read until page 6 and you know, go through how to do this, and then as well as my lecture notes, and then you can do tutorial 8, at least the first 4 questions. Okay, so I'll pause now.